SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering Module 2, and the title of this module is Vapor Power System Part 2. And we are in the lecture number 6, in which we are going to discuss the following topics. First one is impulse turbines, and in fact prior to this lecture we have given elaborate discussions on impulse principles and subsequently how that principle was used, starting from a flat plate to a curved blades, and subsequently through velocity diagrams how power output can be derived. So, in terms of practical utility, we will try to see the realistic version of impulse turbine, how it looks like. So, basically there are two categories of turbines, one is single stage type, other is compounded type. The reason behind these two categories is that many times when in large power plants, when we have steams are available at very high pressure and temperatures, we normally do the compounding, because in a single stage power extractions through impulsive mode gives lots of losses. So, for that reasons compounding is being done, and this compounding is addressed by two configurations, one is through velocity compounding, other is pressure compoundings. So, the topic of discussions for today's lecture will be mainly focused on the practical aspects of impulse turbines, and subsequently how that things we are going to utilize through staging or through distribution of enthalpy drop across each stages. So, this is the overall summary of today's lectures. Now, let us start to understand what we have studied so far in our previous lecture versions. So, what we have proved in that in our previous lectures, that we started with a flat plate in which a velocity of jet which impinges. So, when it is the plate is fixed, then there is no power output, but when we start moving that plate, we saw that we can get 50% of power from the jet. But if you make, instead of plate, if you make a curved blades, we have proved that 100% power recovery from this velocity of jet is possible. And but that is the basic principle, but in a realistic versions, this single curved blade is replaced with array of blades, and these array of blades are exposed for some fluid jet. And of course, these blades are rotating, and we got the velocity of the blade as BB, and once you get this, then this principle we are going to adopt in some configuration or mode. So, this is the realistic version of a in this figure what we have shown is that how that array of blades are organized. So, if you can see these arrays of blades and they are fixed with nozzles, that means there may be a single nozzle or multiple nozzles, and we say that jet is being impinged through these blades, and they after they pass through the blade, the fluid jets comes out in this manner through this passage. The other version of this view looks that this makes this rotor rotating. So, normally we call this a wheel, or in hydraulic term we call it as a impulse wheel, but in our term we will not use the word impulse wheel, rather we will use the word impulse turbine. So, basically what does this do, that the impulse turbine does the rate of change of angular momentum of the fluid in the rotating passage to provide torque on the rotor. And what happens, that initially the fluid enters into this rotor in this initial in the tangential directions with absolute velocity. The fluid flows through this rotor and at a fixed mean radius, and the change in the linear momentum tangential to this wheel or rotor, this gives the tangential force. So, thereby these wheels continuously rotate as long as it receives the steams from the nozzles, and finally the fluid leaves this wheel through tangential direction. Now, just to give some insight of this impulse turbine in a realistic versions. So, they are recognized by their shapes, that means looking at the shape of these blades, we can say it works on the impulse mode, and they have basically symmetrical entrance and exit angle which is 20 degree. Normally these impulse turbines are employed in the entrance of high pressure steam turbine when the specific volume of the steam is low or mainly in the superheated regions. So, if you recall our Mollier diagram, that is HS diagram. So, what we have seen is that when we are looking at this initial condition of the steam, that is state 1, they are in the superheated region, and this fluid expands from boiler pressure to the condenser pressure, and typically this is about 30 bar and this is 0.007 bar. So, under this scaling difference, if you see the steam is already at superheated things, and at these superheated conditions the point to be noted is specific volume is low. These turbines require, another advantage of this, that these turbines require smaller floor areas as compared to low pressure stress condition of the steam. The blades of an impulse turbines are short, they have constant cross sections. The characteristics feature of the impulse turbine is recognized by the fact that most or all of the enthalpies and hence the pressure of the steam, most of the enthalpy drop occurs in the nozzles, that is fixed blaze passage that performs the nozzle actions. So, I will try to emphasize upon the point in the subsequent slides. So, basically impulse turbines are integrated with nozzles that supplies steam to the blades, and most of the enthalpy drop occurs in the nozzles only, and there is a very little pressure drop which is placed in the moving blades, which mainly occurs due to the friction that gives rise to a velocity coefficient term. That is the reason that we say that since the stream is already at very high pressure and temperatures, so there has to be frictions, there will be frictions if there are large number of blades comes into picture. So, hence we have to see that there is some term velocity coefficient that drops in, that gives the losses in the power. But however, this term is quite low, we have seen in last problems that this term is quite low. So that maximum velocity recovery can be possible, because as long as you are maintaining this nozzle angle 20 degree and the flow deflection angle close to 180 degree, this velocity coefficient term will be as minimum as possible. The impulse turbines and the turbine stages are very simple configurations as compared to other configurations. The impulse stages are simple configurations, and there can be a single rotor or multi-rotor turbine arrangements, which means these blades can be connected either to a single rotor or you can have a multi-rotor. When you have a single rotor, we call it a single stage. When you have a multi-rotor, then we may have stages. So, that is the idea of doing the compounding. So, let us start with the first case, which is called as single stage impulse turbines. Now, onwards we will use the single stage impulse turbine as the benchmark, because this is the one most simplest version that version of the turbine that a conventional steam power plant uses. And in steam power terminology, this single stage impulse turbine is the first invention and by a Swedish scientist, and it is called as D-level turbine. So, we have used the word D-level nozzles. So, they are nothing but a convergent divergent nozzles that are used for generating thrust if in nozzle terminology, but in turbine terminology or power generation terminology we say it is a turbine. And because if you look at this arrangement, what we have seen here, these are the blades, single stage array of blades, and direction of the rotation is in this direction. So, we have blade velocity. Then what we have is that we have a nozzle arranged in this manner. So, basically in this figure what it says that this one particular nozzle scatters at least 4 number of blades. So, likewise you can have, if you have a large number of blades, we can think about multiple number of nozzles that can supply the steam to the blades, but at certain angle, and typically this angle is kept as within 20 to 30 degree. We expect 30 degrees so that it caters as many as number of blades. It is very difficult to align theta to be 0 degree, and if this theta is 0 degree, then we will have 100% or 180 degree deflections, but that is in practical point of view it is not possible. So, nozzle has to be arranged at certain angle theta, which is typically 20 to 30 degree, and to cater some arrays of blades. This first point. Second important point, if you see that if you look at the pressure drop, and the pressure drop happens in the nozzle only, because entire enthalpy is exhausted in these things. After that the pressure almost theoretically it should remain constant. After this pressure drop, if you look at the velocity, this velocity is increasing in this nozzle, and side by side once the blade rotates, that means the fluid has transferred its kinetic energy from Vs1 at its initial state to, and it goes to the Vs2, and through this velocity difference we have shown that the work that has come from this work done by the blade would be the difference in the kinetic energy at the inlet and exit. This is what we have been deriving from the velocity diagram. So, this we see that the increase in the velocity occurs in the nozzle, and drop in the absolute velocity of the fluid drops in the blades. So, these points are summarized here, that D-level turbines consist of a single rotor to which impulse blades are attached. The steam is fed through either one or several convergent divergent nozzle arrangements, so that only part of the blades are impinged upon the steam at any point of time. So, there are practical ways that either you can suppose you do not want some blades to not to operate, then we have possibility that we can shut down few nozzles to make this power off, or it means you can shut down some of the nozzles. If you see this diagram, we have shown that overall pressure and velocity of the steam changes in the nozzles and the blade passages. The pressure drop mainly occurs in the nozzles. Kinetic energy of the steam occurs in the nozzle exit, which decreases from Vs1 to Vs2 in the blades. The overall steam pressure and absolute velocity changes are shown in this figure. So, this is about the single stage impulse turbines. Now, we will move on to next concept. So, single stage turbine means you simply refer as we call this as a steam power terminology as D-level turbine. But when you go for the compounding, so first question arises, why do you require compounding? So, normally in modern boilers, that means where the steam generation takes place, we used to look about the pressure availability of around 160 bar. At the same time, temperature also may be very high, close to 300, 400 or 500 degrees centigrades. Now, such a high pressure steam, when it expands to a condenser pressure maybe 0.07 bar or up to atmospheric, what may happen is that there will be enough loss. That means, if you use a single stage mode like a D-level mode, then there will be significant loss. That means, in other words, we are not capturing maximum amount of power from the energy available in the steams, and that is one thing. Second thing, in terms of turbo machinery point of view, there is a limit that that means blades can rotate at certain speed, and typically for a steam velocity of 1640 meter per second, maybe that close to the which is available at 160 bar. For this steam velocity, blade velocity, if you say optimum blade velocity, which is half of this, which is about 820 meter per second. So, rotating at 820 meter per second is also a difficult task. So, for that reasons, what normally is adopted, that if you use a single stage mode, the system will be bulky. Number 2, it will give rise to lot of losses. So, that is normally avoided. So, to overcome these difficulties, two methods are normally employed. One is velocity compounding or pressure compounding. So, basically the compounding word means is staging, that means whatever available steam or enthalpy the steam available to us or energy available to us, you staggered it in stages, and this compounding means nothing but different stages. So, that is the method which is adopted to minimize these losses. So, for that reasons there are two possibilities what we can have, one is velocity compounding, other is pressure compounding. So, let us see what does they mean. So, first one, let us stick to velocity compounding impulse turbine. So, typically when the compounding word comes into picture, scientists try to find out the possible regions or configurations or arrangement how we can make it. They come up with some designs, and one most important designs or with which you can be used as a practical viewpoint is the Curtis turbines. So, it was proposed by Charles G. Curtis while employing the staging of turbine through impulse principle. So, that we call as a Curtis turbine. So, when you say velocity compounded in steam power terminology, we say Curtis turbine or Curtis stage. So, what does he says that we can have a Curtis turbine which is composed of one stage of nozzle as a single stage turbine followed by two rows of moving blades. So, the arrangement looks like in this manner is that there are two rows of moving blades and with one set of stationary blades. So, the alignment is such that the main philosophy is that when the fluid passes the blades, our main philosophy is that we can reduce the velocity as low as possible. So, to do that we are adopting that same concept by through rows of moving blades, but these rows of moving blades have to be fed in a particular manner. So, that is the reason the stationary blades are incorporated. So, these stationary blades are many books interpret as a guide vanes, means it has they have no role, but rather the exit from the first stage of moving blade will be redirected to the entry of the next stage of moving blade. So, these are many books refer as a these are called as guide vanes, but in our term we say these are stationary blades that they do not rotate, but these are like a guide vane. And of course, at the entry stage that entire steam or power is supplied through a single nozzle or array of nozzle. Same concept is applied here, but instead of if you see that pressure stage, pressure only drop only occurs in the nozzles, rest of the things after that pressure remains constant. But if you look at velocity, the drop in velocity happens in only moving blades. Like here from first stage of moving blade we have from Vs1 to Vs2, then stationary blade does not do anything, there is no change in the velocity. Then from last row of second row of moving blades it changes from Vs through to Vs4. Through this process velocity drop happens. Now, if you do that, the drop in the velocity if you make in a very step by step manner or you can do in the stages, there is a chance that it is possible that thermodynamically it is proved that maximum utilization of energy is possible. So, this is how the concept of Curtis stage when Curtis turbines employ. Curtis turbine by default it is a velocity compounded impulse turbines. Then moving further, if you want to analyze this in terms of velocity diagrams. So, this particular figure shows the schematic diagram of inlet triangle and outlet triangles, and this is the first set of moving blades which is here. Moving blades has same fluid Vb. The first set of first stage, these moving blades moves at this velocity Vb. Again in the other case also this same velocity Vb. Now, to have this same velocity, the fluid has to be organized in this manner. That means more steam quality. That means if you see that blade velocity is Vb in everywhere in the velocity diagram. Then what does this stationary blade does? It simply guides the fluid to have a smooth entry at the next stage of moving blade. Now, one more important thing factor, like we have emphasized here, that there are possibilities that that is a drop in the velocity of the fluid from in this velocity diagram. Like for example, in ideal conditions this Bs2 and Bs3 are equal. So, Bs2 is where? Bs2 is the blade that leaves from the first stage of moving blade, and Bs3 is the entry for the second stage moving blade. So, we can introduce the term velocity coefficient or Kv, which takes care this ratio, as which says, which we can quantify that this is the amount of the fluid that enters. That means, we can precisely say what velocity the steam enters in each rows of moving blade. Now, once we have everything, then we can calculate the work transfer by impulse principle, momentum impulse principles. Then of course, we can calculate the blade efficiency and stage efficiency in the similar manner what you did in our last lecture. Just to give the mathematical insight about the work output that we get from a Corti stage, this is the general expressions that if you recall our previous study, previous lectures, our work transfer was focused, or we have derived that work output from a impulse blade is m dot by 2 into whole bracket Vs1 square minus Vs2 square plus Vr2 square and minus Vr1 square. So, we have showed that for the time being, if you just ignore this term right now. So, if you have only one set of blades, this is the work output from the blade. But what happens that if you have a pure impulse mode, the relative velocity terms will becomes 0. So, we say that this work output is only pure impulse mode. Now, in this case, since we have two sets of moving blades and each of them will have a velocity triangles. So, in the first case we have velocity triangle which involves Bs1, Bs2, Br1 and Br2. In the second case we have Bs3, Bs4, Br4 and Br3. So, this work gets added up, that means we are recovering the work in a staged manner. So, this gives a higher power output. So, this is how the Corti stage of recovering power from the steam is all about. Now, once we have work transfer, then we can find the kinetic energy, and remember that for all these cases we have used the same nozzle for all the blades. So, kinetic energy at the inlet is always half mv S1 square. So, once we have blade efficiency, then we can find out the stage efficiency. Stage efficiency means enthalpy drop of the fluid for the whole stage. That means, then when the fluid enters here and leaves here, what is the drop in the enthalpy in this whole stage. So, this is how we get the stage efficiency. Now, in same philosophy we can extend it for any number of rows. So, like there we have only two sets of moving blade and one set of stationary blade. Now, we are coming here as three sets of moving blade and two set of fixed blades. So, same way we start with Bs1, Br1 which enters and which leaves it Br2 and Bs2, and this gives a blade velocity Vb. Now, for the next set of moving blade it is Bs3 and Br3 that is entering, and it gives the blade velocity Vb. Now, and for these two we have Br4 and Bs4. So, this gives the velocity Vb, and subsequently when you go to the last one, it is Bs5 and Br5 and it gives Bs6 and B6. So, till how long we can do that when this velocity which is impinging, now it has, if you see, this magnitude is very less. So, in a realistic way, if you draw the vector diagram appropriately, you can see that the length of this magnitude or magnitude Vs6 is quite low. So, that means you have captured maximum energy from the fluid, because its magnitude has reduced substantially. That means, if we have this Vs1 length of value and finally Vs6 becomes an insignificant number. So, to think about some kind of a realistic mode, basically speaking, we have using n stages to extract the power. So, ideally speaking, one can think of n number of stages, and if you say if there is just one stage, then the optimum velocity that gives maximum power would be Vs1 cos theta by 2, that you have already derived. Now, if you have n number of stages, that means n number of rows of moving blades, then optimum velocity also gets reduced. That means, for same energy extractions, we can operate with a lower blade velocity. Same power can be extracted at lower velocity. So, this is the advantage that we get when you do velocity compounding through Cortis. And what other advantage or maybe geometrical advantage that we get are like this. So, when you do the staging with successive increase in the blade angles, that results flatter and thinner blades. That means, when we go towards the last row of blades, it becomes thinner, because there is no significant stream velocity which is available at that end. So, that gives an advantage. We can say that exit velocity we can bring down to close to 0 for ideal power generation systems, and through these stagings we can say that we can operate the fluid, we can extract same power with relatively less blade velocity. Now, when you do this highest to lowest pressure stages, typically when you say 3:1, we say it is a 2 stage Curtis, and it becomes, when it becomes 5:3:1, it is a 3 stage Curtis, then it becomes 7:5:3:1 means 4 stage Curtis turbine. But what I have seen is that now when you go for higher number of Curtis stages, practically it becomes uneconomical, mainly because that means when you go towards number of stages, although you are trying to reduce this Vs6 to be 0, but towards the end side fluid do not have sufficient momentum to drive this blade. So, basically when Curtis stage going beyond 2 is normally avoided. So, that means that point of time this velocity compounding will not be an effective mode. So, you have to look for some other methods, which means that when we have Curtis stage more than 2, that means we have very high pressure steam and we are thinking of going for higher stage or 4 or 5 stage Curtis, it becomes uneconomical. So, that means velocity compounding is not a feasible option as far as its practical utility is concerned. So, then what do you do? Then we go for the next alternative. So, what is done as pressure compounded impulse turbines. So, here this compounding is done in same way, but relatively, that means we have availability of steam at very high pressure, superheated pressure, high pressure steam as well as superheated steam, and then we are going to extract its power through its compounding. So, here the entire idea is that if you want to do through pressure compounding mode, how do you do? And this velocity compounding tells that Curtis stage beyond 2 is not economical, but at that point of time there are critical requirement that your blade speed at 2 stage is also too high. So, this means that the issues of high blade velocity in the single stage turbine is elevated by incorporating nozzles in each stage, so that enthalpy drop is divided into many single stages. So, basically pressure compounding is a method in which each moving blade will be associated with its own respective nozzle. That means, same nozzle will not supply the fluid to all the moving blades, rather we will have a different nozzles for each set of moving blade. Now, if you do that, how it works then? So, this works in a same manner, that means if you look at this set of moving blades, it starts with some pressure, there is a pressure drop in the nozzle, and across this moving blade there is no pressure drop, and again it till goes, and when it goes to the next point, that is next, that means this same fluid is being exit from this is being fed to this nozzle. Now, when the exit fluid is fed to the next rows of moving blade through another nozzle, then you see that there is a second stage pressure drop. So, here pressure drop is done in stages, and side by side if you look at the velocity plot, in the first stage the velocity increases, in the moving blade there is a drop in the velocity, then in this portion there is no change in the velocity. Next rise in the velocity happens when there is a next set of pressure drops. So, this keeps on happening for subsequent stages. Now, this concept of pressure compounding is normally referred with the viewpoint of steam power terminology as rate 2 turbine. So, here it says that the total enthalpy drop is divided among many single stage impulse turbines. The inlet fluid velocity to each stage are equal with a reduced enthalpy drop, and we can find out this from this figure. Already I have explained that the enthalpy drop for stages is same, but not the pressure. Now, to give more emphasis that how you need to think about in a realistic number, what it says that suppose you have availability of steam which is about 70 bar 800 degree Kelvin, and it has to be expanded to condenser pressure for 0.07 bar, and which carries about enthalpy of this. So, we can divide this enthalpy in 3 or 4 stages, which is comes about 337.5 kilojoule per kg, but we can think of this to happen at different pressure drops. In the first stage we can have 45 drop in pressure, 18, 6 and 1. So, that means instead of going for 0 velocity we are going to close to atmospheric pressure. So, this is how the requirement is. So, in this process what happens that the inlet velocities to the nozzles becomes we can calculate from the nozzle equation, simple nozzle equation, as twice into total enthalpy drop divided by n, where n stands for number of pressure stages. And this gives a complete clear picture how staging is done in a pressure compounding mode. You see here there are for each rows of moving blades there are fixed set of nozzles, and each one call it as a stage 1. For stage 2 another set, for stage 3 another set, likewise the pressure compounding is done. So, in other words, we can say that each of these one can be viewed as a single stage impulse turbine, and correspondingly their velocity diagram is drawn, and this turbines we call as a rate 2 turbine. And finally, the significant point that we need to emphasize here, that there is exit velocity of fuel is for all the stages is 0, and which corresponds to optimum blade velocity. The nozzle of each stage receives steam discharge from the previous stage, expands it, redirect it to moving blades. So, this is the main philosophy behind the pressure compounding of impulse turbine. And if you look at certain advantages, there are some advantages like we have reduced blade velocity in each stage, that is because blade velocity if you see in each stage it gets reduced because it receives the fluid at a, because the nozzle for each moving blades will have a different entry velocity. There will be reduced steam velocities due to frictions, equal work among all stages. So, these are the advantages that we can get, but there are disadvantages is that unavoidable steam leakage and large number of stages when you go for them. So, when you have go for number of stages in a pressure mode, there will be unavoidable steam leakage and large number of stages. So, unless and until your this concept is implemented where efficiency is important, we do not go for higher stages pressure compounding, rather we are satisfied with at least 2 stage Curtis mode of velocity compounding. So, if efficiency is more important than capital cost, then probably this particular idea of pressure compounding is a better approach. So, this concludes this theory of compounding under impulse principle for steam turbines. Now, we will try to solve the similar numerical problems based on our discussion today. So, in our previous lecture we have similar problems, but here it is proposed to have the problem based on the stages. So, basically speaking, the problem is based on a impulse turbine which works on number of pressure stages. So, we mean that this is a pressure compounding type impulse turbine, and that means when you have pressure compounding, which means each one will have own sets of nozzles and moving blades, and we need to concentrate on one particular stage. So, one thing that we have seen here that now in the first go we can assume that each when you are talking about number of stages, the enthalpy drop is divided. So, we can say equal number of stages. So, basically each stage gives equal amount of work. So, with this assumption we will proceed for solving this particular problems, but here our attention will be done only for one stages, and for that one stages we are going to draw this velocity diagram, and since it is an impulse turbines, so velocity diagrams are concentrated with respect to one particular blades, and this particular blade will have some inlet triangle and we have outlet triangle. So, for this we have nozzle angles theta, we have the blade angle phi, then we have the fluid exit angle delta and this blade angle gamma. Okay. So, before that things you have already understood what is this inlet and outlet velocity triangles. Now, let us to solve these problems we need to combine these two diagrams, and you have to draw with same blade velocity Vb, we have to combine inlet and as well as the outlet velocity triangles. So, what I am drawing is the combining both the velocity triangles in a single graph or single diagrams, which is going to look like this. So, this is your Vb and this is Bs1 and Br1, and for same velocity we have this outlet velocity triangle should look like this, which is Br2. So, this will be somewhere in this Br2, Bs2. So, we have this angle delta and gamma. So, we say it is, let us say this is gamma, this angle is delta. So, then we can drop one vertical to make it a right angle triangle. We can name this triangle as A, D, C, B, P, R, and to precisely make this angle as we say phi, this will be phi, and phi is this angle. Then we have this gamma, means this will be gamma, and this angle is theta, and this angle is, if this is delta, this angle will be 180 minus delta. Okay. So, once you have drawn this angle, then it is able to, we have need to find out, analyze this velocity triangles. But what has the data has been given is that if you see, we have this velocity, mean velocity Vb, which is 130 meter per second, velocity of the steam entering the nozzle, that is Vs1 330 meter per second, nozzle angle in the first stage, that is theta is 20 degree, blade exit angle is 30 degree, that means this is nothing but your gamma. Gamma means, that means this gamma, because when the fluid exits, it exists with that relative velocity. So, at the exit state it is Vr2, so it is gamma is 30 degree. This is already done. Then what we have given is nozzle efficiency as 85%, velocity coefficient Kv, that is VR2 by VR1 is 0.8. So, this data is given. We need to find out work done per kg of steam and blade velocity. So, to start the solution for the part A, we rewrite the equation, that is work done. W dot would be m dot Vb. So, this is the basic equations, Bs1 cos theta minus Bs2 cos delta. So, what information we have? We have only Bs1, we have Vb and m dot. M dot means you can work done, if you say per kg, then it becomes W dot by m, that is Vb into Bs1 cos theta minus Bs2 cos delta. Of course, we do not know these numbers. So, this data and this velocity triangle will help us in estimating this angle. So, let us try to concentrate inlet. So, in this inlet triangles, we write AD as BR1 sin phi, that is equal to BS1 sin theta, and similarly CD is equal to BR1 cos phi, that is equal to BD minus BC. So, this means BR1 cos phi is equal to BS1 cos theta minus BB. Then both the two equations will give you tan phi is equal to Bs1 sin theta divided by Bs1 cos theta minus Bb. So, we have Bs1 as 330, already data is given, sin theta is sin 20 degree, that is nozzle angle, Bs1 is 330 cos 20 minus Bb is 130. So, this will give you tan phi as 0.62, which implies angle phi we get as 32 degree. So, this angle is known. So, remember this angle is known. And then let us see that we have these relations. Now, Br1 sin phi is equal to Bs1 sin theta. So, this will give you Br1 is equal to Bs1 sin theta divided by sin phi. Putting this number, we have 330 sin phi is 32 degree divided by, this is sin theta, theta means it is 20 degree by sin 32. So, Br1 would be, will get 213 meter per second. Once you know this, you know Kb is equal to 0.8. So, this means Br2 would be 0.8 times into 213. So, this is 170.4 meter per second. Now, we will move on to the outlet triangle. So, from this outlet triangle, if you recall our triangle which was drawn in the first page of this problem, we can rewrite as PR is equal to BR2 sin gamma, that is equal to BS2 sin 180 minus delta. So, I am recalling this particular triangle and this outlet triangle. So, from this outlet triangle we get this information. So, if you can write it here itself from this outlet triangle, we can say PR is equal to BR2 sin gamma that is equal to Bs2 sin 180 minus delta. So, this means Br2 sin gamma is equal to Bs2 sin delta. So, this is one expression we get as Pr is. Other expression that we can get is this Cr. So, Cr is equal to Cb plus Br. So, Cr is nothing but Br2 cos gamma is equal to Vb plus Bs2 cos 180 minus delta. So, this is we get from this outlet velocity triangle. So, now let us use these two equations here. So, what we can start from these expressions, we have two equations. One is Br2 sin gamma is equal to Bs2 sin delta. Second one is Br2 cos gamma is equal to Vb plus Bs2 cos 180 minus delta. So, this equation now it is because cos 180 delta is minus cos delta. So, it means Br2 cos gamma is equal to Vb minus Bs2 cos delta. So, we have do these two equations. So, this will give you tan delta is equal to Br2 sin delta. So, tan delta is Br2 sin gamma. So, these two when you take the ratio Br2 sin gamma divided by Vb minus Br2 cos gamma. So, these two equations now here we have already found out Br2 as 170.4 meter per second. Your gamma is 30 degree. So, this will give you tan delta as minus 4.84 and delta would be 102 degree. And here you will see that this term will be a negative term because denominator term will be a negative term, and that means this number would be 85.2 divided by minus 17.6. So, the ratio gives tan delta as minus 4.84. So, this gives delta is 102 degree, that means this delta is greater than 90 degree. So, this gives an added advantage that we will see that how this delta greater than 90 degree helps us in calculating the power. So, once we have this delta, then this Vs2 can be calculated, that is equal to Br2 sin gamma by sin delta. So, these numbers we know, that is 170.4 sin 30 divided by sin 102. So, this number is 87 meter per second. So, once we have this, then we can calculate what is W dot by M dot, that is Vb into Bs1 cos theta minus Bs2 cos delta. So, by putting this number we say 130 into 330 cos 20 minus 87 cos 102 degree. So, this cos 102 degree is a negative term. So, this will add, that is 3110 plus 18. So, the final answer, that is work done per kg of steam, is 42.64 kilojoule per kg. Okay. So, this first part answer is done. Then going to the blade efficiency, so we say W dot by M dot is 42.64 kg kilojoule per kg, and if you see blade efficiency, that is eta blade would be W dot by M dot divided by BS1 square by 2. So, this 2 into 42.64 into 1000 because it is kilojoule divided by BS1 is 330 meter per second into 330. So, this number is 78.3%. So, we say blade efficiency is 78.3%. Now, for the second part, the steam on the first stage is 20 bar 250 degree centigrade, condenser pressure is 0.7 bar. So, basically we have to find out what is this enthalpy drop. So, for that reasons we have to draw this either enthalpy Mollier diagram or temperature entropy diagram. So, you can see that steam which is available and the drop takes place, that is 2s 2 1 to 2. So, enthalpy drop we can say for part B, this is 20 bar 250 degree centigrade and this is 0.07 bar. So, find out 20 bar 250 degree centigrade, which will implies H1 as steam table will give you H1 as 2902.3 kilojoule per kg, and in this process had it been isentropic we would have S1 is equal to S2S, that is 6.6546, and this S2S is nothing but your SF plus X into SFG, and SF and SFG has to be calculated at 0.07 bar. So, we have SF as 0.5582 kilojoule per kg Kelvin, SFG would be 7.7198 kilojoule per kg. We also require enthalpy HF is equal to 163.16 kilojoule per kg, and HFG is 2409.54 kilojoule per kg. So, we have these equations. So, from this we will give you X as 0.7757. Once you know the X, we can find out H2 is equal to HF plus X into HFG, and this number is 20 that is H2S. So, this 2032.9 kilojoule per kg. Now, turbine efficiency is H1 minus H2 divided by H1 minus H2S, that is given as 70%. So, we have H2S, we have H1. So, we can find out what is H1 actual enthalpy drop. So, actual enthalpy drop is now becomes 612.6 kilojoule per kg. So, basically the steam which is available at 20 bar and 250 degree centigrades has to drop this many enthalpy to arrive at the condenser pressure. But our work done per kg of the steam is for about 42.64 kilojoule per kg, which means that per stage we are able to recover only 42.64 kilojoule per kg. So, this means number of stages, by assuming equal stage efficiency and work done for all stages, would be ratio of delta H total divided by delta H stage, and that number will be 612.6 divided by per stage 42.64. So, this comes approximately 15 number of stages. Hence, we require 15 number of stages to drop about 612.6 kg enthalpy of the steam by equally dividing them with work output as 42.64 kilojoule per kg. So, ultimately in the end we say that this we can quantify this number of stages as 15. That means 15 number of stage is being used, and it is nothing but a pressure compounded impulse turbine. So, with these discussions, thank you for your attention.